Okay, so finishing up the RSA encryption bit. So this is the content of chapter 9. Um, I had mentioned uh, the end of lecture yesterday that uh, since we're pretty hopeful about the security of this algorithm, meaning that when we said something was computationally infeasible. So if it was computationally infeasible to break this, um, what we meant by that is that using current tech, it would take many thousands of years to factor some product of these cryptographic primes. Okay, so um, the uh, uh, the thing is that in certain special cases, it is possible to essentially break this encryption um, by avoiding the issue of computing or of factoring in or computing the decryption key D. This has a workaround so that it's not actually that big of a deal, but to see how this actually would work or what you might do. So one potential attack when the message is not too long. Okay, so here's one potential attack on RSA when the message M is not too long, i.e. M doesn't have that many digits. Okay. So the thing that I'm going to list is going to be something that's slightly less obvious than might be the first thing that you mentioned. So I'll mention that at the very end. Well, maybe I'll go ahead and mention it now and then talk about it again later. So suppose that M is like fairly fairly short. So we'll say suppose M has say like 6 digits, right? Um, if M has 6 digits, then the idea is that if I intercept a ciphertext computed using M, then the ciphertext likely has about the same number of digits as M, so the ciphertext is also going to be short. So what is the idea? The idea basically is I intercept ciphertext. I say, well, this ciphertext length is going to be like roughly the length of M. And so what I do is I just take every potential message, say up to 10 to the 6 or 10 to the 7, and I encrypt it since I know how to encrypt. It's public key cryptography, so I know what the encryption key is. So I can take every single one of those and just encrypt them. Uh, and and I do that, and then I compare that list I get with the ciphertext, right? And when I find the thing that has produced the ciphertext, then I've recovered the original message, right? I've seen what M has given rise to that ciphertext that I've intercepted. So that's kind of the stupidest, like most brute force way of going about it. And in some instances, that way will be quicker than what I'm about to do. But I'll give you an example here in like 10, 15 minutes of when this method I'm going to list is going to be slightly faster. So yeah, and ignore any growling cats in the background. I hear my cats are about to fight. So stop it. Hold on. Stop it. Okay, have to pacify the angry cats. Okay, so anyway, uh, the idea is this. Um, say m has fewer than 16 digits. Okay. All right. So I want to find m from its ciphertext C. C is, which will have approximately as many digits as m. Okay, so I want to find m from its ciphertext C without factoring in or finding d. Now, even though I didn't prove this, I said this previously, that factoring in or finding d are known to be equivalent difficulties. Okay, so you're not better off choosing one or the other. It's basically the same type of thing. So I make two lists. Okay, what are the two lists that I make? So my first list is x to the e being the encryption key that's public, right? Mod n is also public. All right, so x to the e mod n is something I can compute for all x's. So with all x from 1 to 10 to the 9. Okay. So I make a list, x to the e mod n, for every x between 1 and 10 to the 9. Okay. You might say, wait, if m is 16 digits, why am I only doing this up to 10 to the 9? So I'll get to that in a second. Okay. The second list I make is my ciphertext C, which I've intercepted, y to the minus e mod n. Okay. With y being in that same range. Okay. Okay. So I make two lists. So first list ranges over all x's between 1 and 10 to the 9, and it's x to the e mod n. Second list is my ciphertext C times y to the minus e mod n, y ranging over that same range. Okay. Now, I compare lists. If there is a match, i.e., since both of these lists are mod n, if x to the e is congruent to c times y to the minus e mod n, then x times y to the e is congruent to c mod n. Okay, so now you see what it is that's going on here. But since both of these are between 1 and 10 to the 9, right? Well, x times y is between 1 and 10 to the 18. And that is going to be smaller than n. Then m is equal to x times y. Right. So let's describe what it is that we've done here. So we've set up once you see what's going on here, then it's clear why we set up these lists to work like this. So starting here, if I just told you we're looking for a form of m where m is factoring as some x times y, with the x and y being between 1 and 10 to the 9, Okay, so so we're thinking of m as factoring um, as a product of two integers of at most 9 digits each. Okay, and then we're, of course, to to verify that this is going to have the same property as m, since m to the e has to be congruent to this ciphertext, since that's how you encrypt m in the first place. This x times y to the e is congruent to that same ciphertext mod n. The idea here, is that since x and y are of these sizes specified, m has to be equal to these things. So this has to be the original message. So the question is, why does this work? Well, so it's clear at least what's going on here, where we are just setting this up so that x times y to the e is the same ciphertext you get by raising m to the e. Okay. But why would this work? Well, since m is at most a 16-digit number, saying that it might factor as a product of two integers that have at most 9 digits is not it's not that unreasonable of a statement to make. Now, this is not guaranteed to work. You're not guaranteed to have a match like this. Okay. So this by no means has to happen, but it's not unlikely that for such an m this would work out in this way. Okay, so that you could do this. Okay, and rather than actually rewrite all these large numbers again, I am just going to show the example. So looking at this example in the textbook, so we're going to use the same encryption that we did going forward, encrypting and decrypting our original message in yesterday's example. So say that you know what the encryption key is for an RSA method, so it's 233. And you know what n is. N is this large number here from yesterday. Okay, so we don't know p and q, right, that multiply together to form n. We don't, of course, know phi of n, but we've intercepted the ciphertext. Okay, we have intercepted the ciphertext. There it is. It's this large number. Okay, and so let's say that we suspect that our message m is less than 10 to the fifth. Okay, and so we hope that it factors as a product of two numbers that are less than 1,000. Okay, that's our hope. Okay, and so we make two lists. So we make the list x to the e mod n, so x to the 233 mod n, this large number, where x ranges from 1 to 1,000. And our other list, of course, is our ciphertext, this large number c, times y to the minus 233 mod n. Okay, again, where y ranges from 1 to 1,000. Okay, and it turns out that generating these two lists and comparing them, we get a match. So 74 to the 233 is congruent to c times 407 to the minus 233 mod n. Okay, and therefore, this ciphertext is congruent to 74 times 407 to the 233, but 74 times 407 is 30,118. And so we recover 30,118, which is the message car from yesterday, right? This is our message that we encrypted. Okay. So, that might be a little bit alarming at first, since we have this supposedly really robust encryption method that we've managed to break in this case. So what is the alternative? Like, what is the solution to this? Well, you could say, well, we could just always send really, really long messages, right? So if you always sent really long messages, then yeah, it might take a little bit longer to encrypt, but they would not be susceptible to attacks like this, because the list that would have to be made would have to be enormous. And so So maybe I just want to send really, really long, really, really long messages only. But the reason that's alone is not super practical on its own is that a lot of times I want to use RSA specifically to send securely a key that might not be that large for some other encryption method like a symmetric crypto system, right? So a lot of times the message that I want to send is not going to be that long. So how do I deal with it? The idea to prevent this, we can introduce fluff digits, right? That's not an official term. I just made that up. The idea is we just put in some extra digits that are meaningless, and as long as as long as the person that we're sending this to understands that we're adding extra digits, then everything is fine. In fact, you can even tell malicious actors that you're adding extra digits, and there's not really anything they can do to fix that. Because the addition of those extra digits to begin with already makes it just too difficult to handle. So for instance, going back to this example here, so it says, however, suppose Bob changes his message to M is 11110301118111. So he's added extra ones at the beginning and end. And end of this. Okay. So then M can't factors this unless X and Y have many more digits. So the attack is going to require longer and longer lists. And of course, there's no reason to stop there. You could make this even longer. So and as it says, Bob can even tell everyone that he's added the extra digits. Okay. So the point is, you could add some fluff digits, like a bunch of ones at the to the front of it and to the back of it, and encrypt using that number instead. And that fixes attacks like this. The other example that I mentioned is say that you knew that M was less than 10 to the fifth. The easiest thing to do there is to just encrypt every single digit, or every single number up to 10 to the fifth using the public encryption key. So encrypt every single one of them. One of those will be equal to the ciphertext you've intercepted. So whichever one generated the ciphertext you intercepted, that's your M, right? That's it. So so that's the easy way to do it. But of course, the problem is that if you up the digits of M, so if M has 16 digits, that becomes a lot less feasible, because now you would have to encrypt a lot more numbers, right? And the longer that M gets, the more and more infeasible this becomes to attack in this way. Okay, so one last thing I wanted to say about RSA encryption before moving on is the application of RSA encryption. We don't need to really modify it at all to digital signatures. So the idea of having a verifiable digital signature, so that is a signature that's been performed remotely for some document, right, that needs to be signed, that you can be sure the document in question has been signed by the person that you're intending it for, right? So application of RSA to digital signatures. Okay. All right, so here is the setup. So Alice applies for insurance. She calls up her broker, Bob. They negotiate, and he sends her a contract. Okay, so normally, of course, you would have this contract printed, it would be mailed, and then it would be signed, either in person, or if it wasn't in person, it would be mailed to her. She would sign it and send it back. But say for whatever reason it's not feasible to do that. And so say that, instead we want to be able to sign this digitally, right? So just simply via the internet or something. And so the idea is that you really need a process that guarantees that the person signing for Alice really is Alice, right? and that no one is able to basically forge this digital signature. Okay, and so how would this work? So the idea is we have a document that we'll call M that takes the role of our original message. Okay, so say M is our insurance policy that I just mentioned. Okay, so some kind of insurance policy. Okay, so Bob wrote this for Alice, we'll say. And Alice is the one that needs to sign this document and return it, and Bob can then check that Alice is actually the one that signed it. Okay, so Alice chooses two primes, P and Q, multiplies them together, so forms N, which is P times Q, already looking very familiar. Then she chooses an E with, you already know what's coming, GCD of E and phi of N being 1. So E is relatively prime to phi of N. And E is going to be strictly between 1 and phi of N. Okay. So now Alice then computes via the extended Euclidean algorithm. So she computes D such that E times D is congruent to 1 mod phi of N. Okay. So she publishes E and N, keeps P, Q, and D private. So far the setup is exactly the same as the normal RSA encryption algorithm. So then what happens? Okay, so Alice then reads the document. If she agrees to sign it, she creates her digital signature. So then Alice generates her digital signature by computing M to the D mod N. So another way of writing this is her digital signature we'll call S. That's congruent to M to the D mod N. Okay. So Alice now sends the pair MS back to Bob. Okay. All right. So, what does Bob do to verify what's going on here? So, Bob takes the M and S that she has sent. He has access to her public key, E, right? So, E and N are public. Okay, so he has access to both E and N, so he looks that up wherever she's put it. And then he raises her digital signature S to E and verifies that it's equal to M, right? So Bob raises S to the public key E. So S to the E is congruent to M to the D to the E. So that's congruent to M to the ED, which by our proposition from yesterday is M mod N. Right? So what is it that's happened here? This is just RSA in reverse, right? So this is just RSA in reverse, where the going forward bit, instead of encrypting with E, the encryption is done with D, the decryption key, and the decrypting is done with E, the encryption key. All right, so this is just RSA backwards. Okay. So that's how this works. So writing that out in a nice form. So RSA digital signatures. Let's do the quick version. So public info. And this is Alice's public info. So N and E. Alice's private info. D, P, and Q. Right. Alice's signature is S, which is M to the D mod N. Okay. So the signed document is the pair MS. So that gets sent back to Bob. The verification process then is simply checking that S to the public key E is M mod N. So that's the question. Okay. So how does this work from the standpoint of making sure that this is secure? Well, the idea here is that if someone wanted to butt in and somehow, insert themselves into this arrangement so that they wanted to forge Alice's signature on some other document or something, what would they have to do? So first off, they would have to draw up a different contract, which is like some different M, so M sub 1. And forge her signature. But in order to do that, you would have to find some other signature S sub 1 such that S sub 1 raised to that public key of E was equal to M mod N, right? So to forge, what would be needed is you have a different M sub 1, S sub 1, such that S sub 1 to the E is congruent to M sub 1 mod N. And finding this pair is hard. Infeasible. Okay. So this is computationally infeasible. Okay, using the same term from yesterday. Here's another thing. Of course, you could say, wait, but what if someone started with some S sub 1 and then simply defined S sub 1 or S sub 1 to the E to be M sub 1, right? Okay. Mod N, right? Maybe I should do that. That's a weird symbol. And I write mod N here on the left, right? So what if someone started with an S sub 1 and just said, yeah, okay, I can come up with a pair. I just define M sub 1 to be the thing to work out in this way, right? So it's not infeasible at all to find this pair. Boom, I did it, right? I found this pair here. The problem with this is that you're taking your signature S sub 1, raising it to the E, and that's how you're getting your M sub 1. But think about this in the context of what's going on in this problem. That M is the document you're trying to cook up, right, to place a forged signature on. The idea being that the document in question would ideally for you, right, have something that you've added to it or would be of some particular form, right, that would be beneficial to you. That's the entire purpose of you doing this. The idea being that this M is the thing that you're cooking up, right? So defining your M backwards in this way is essentially letting this contract that you're forging a signature on be like randomly generated, right? It's just going to be a complete gibberish document, right? Because you're just taking whatever you get from this from this exponentiation. So it's not going to produce anything that's intelligible at all in general, right? So that's why this process is secure. Okay. So note again, this is just RSA backwards. So you are encrypting with the decryption key, and so the decrypting can be done publicly with the public key. Okay. So that is it for now for RSA encryption. We are going to talk about other public key encryption methods. We're gonna be returning to crypto methods throughout like the remainder of these 2 weeks. We'll be touching on those again. So we will return over and over and over again to discussions of this stuff. Since most of these applications once we've built up slightly more machinery, we can jump back into some other application that requires that extra bit of machinery we've developed. So if you look at how the book is laid out, starting after the end of chapter 6, chapter 7 was dealt with cryptography because it relied on all the machinery that was developed before that. Chapter 8 was Fermat's and Euler's and Wilson's theorem. So Euler's theorem specifically, of course, was needed before we could do RSA encryption, but that's basically all we needed, essentially, was Euler's theorem. And then, now that we've done this, we're going to talk about a little bit more here before we get into what is going to be like the big kind of like deepest thing that we prove in this. Well, I'm not sure I'm going to prove it. I may skip the proof on it, but it will be the deepest thing that we talk about in this course coming up in chapter 13. But we got to develop some stuff first. Okay, but like I said, we will return. So basically every other chapter flip-flops between a little bit of mathematical background stuff and then its applications to some type of cryptography. So we're going to do so 9 was a crypto chapter. We're going to skip chapter 10. We're going to do chapter 11, and then we're going to do chapter 12, which is another crypto chapter, and then we'll do chapter 13, which is a non-crypto chapter, and chapter 14 is again crypto chapter. So that's kind of how this textbook goes. Okay. All right. And so moving right along. Chapter 11. So title of chapter 11 is Order and Primitive Roots. We're going to jump right into the discussion of order. So here's a quick definition. Let n be a positive integer. And let the GCD of a and n be 1. Okay. Then the order of a mod n, okay, is the smallest positive integer m such that a to the m is congruent to 1 mod n. Okay. So, we write this integer as the order of A mod n. That's how it's written. Yeah, that's an ORD. Okay, so we read that order of A mod n. Okay, so this might seem like a slightly strange definition at first because I'm defining this thing, although you might want to ask a question before you've talked about what to call it. First of all, does such an integer like this always exist? Right, is an immediate question. So question, given A and N, can you always find, so given A and N satisfying the definition, does, or I could say, is order well defined, right? Is the order of A mod N well defined? Right? Meaning, is there any ambiguity here? Does this smallest integer ever exist, or can we just end up with some A such that A to any power is never 1 mod n? So the answer is Euler's theorem. Oh, why did I put the apostrophe there? Euler's theorem says that A to the phi of n is congruent to 1 mod n. So there has to be some smallest integer for which this is true, because phi of n works. Okay. So order always exists, and order is always less than or equal to phi of n, right? Written in a better way instead of writing words, right? So the order of A mod n is less than or equal to phi of n, right? So it exists, and I'm off screen. So it exists, and it is bounded above by phi of n, okay, by Euler's theorem. So that's nice. Okay. We can look up, or we could do a couple of examples here illustrating the order of some element. So here's an example. So 2 to the 6 is congruent to 1 mod 9. Okay. And 2 to the I is not congruent to 1 mod 9 for I between 1 and 5. So this is the first, that is the smallest power of 2 guaranteed to be congruent to 1 mod 9. And so the order of 2 mod 9 is 6. Okay. All right. So of course, what's something to note here? There is, once you have reached the order, right? If you're taking some A and you're exponentiating it mod n, once you exponentiate it eventually to its order, right? Maybe you got to go all the way to phi of n, okay? But once you get there and you apply Euler's theorem and you do that, then successive multiplications by A start to repeat this cycle, right? So here, right, you would have 2 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, but then 2 to the 7th would be 2 to the 6 times 2, so it'd be 2 all over again, and so that cycle would repeat. Okay, so if you've had any experience with algebraic structures, then you already are familiar with this concept, and you likely have already noted that it's not an accident that we use this word order here, since that is the same word used in the context where this shows up a lot. So anyway, so this is order. Now, this might, just looking at it like this, getting this very basic property of the order here, you might, of course, have ideas that, thinking of it as I did before with listing out my list. So what do I mean listing out things? So I have 2. So 2 is just congruent to 2 mod 9. That's 2 to the 1st. So that's congruent to 2 mod 9. And then 2 squared is congruent to 4 mod 9. And 2 cubed is congruent to 8 mod 9. Okay, and 2 to the 4th is congruent to 16, which mod 9 is 7. Okay, and 2 to the 5th is congruent to 32, which mod 9 is 5. And then 2 to the 6th is congruent to 1 mod 9. But then restarting here, right, 2 to the 7th is congruent to 2 to the 6th times 2, so that's just 2 mod 9. And this cycle repeats, right? So thinking of it in that way, you could think, well, if I generate this list, then if I just go through and say, okay, 6 is an exponent that causes 2 to be congruent to 1 mod 9 when I raise 2 to 6. So 2 to the 6 is congruent to 1 mod 9. I already know that. I computed the order of 2 mod 9, right? But then what's the next one in this list that's going to be congruent to 1 mod 9? Well, just going through this cycle, the next one, of course, is going to be 2 to the 12, right? So 2 to the 12 is going to be congruent to 1 mod 9. All right, so using that same example, 2 to the 6 is congruent to 1 mod 9. And 2 to the 12 is congruent to 1 mod 9. And what would be the next in that list? Well, they would cycle through again, and the next one in the list would be 2 to the 18 is congruent to 1 mod 9, right? And then what would be the next one? 2 to the 24 is congruent to 1 mod 9, and this would continue. Well, what do you notice about these exponents? I mean, very obviously these are all multiples of 6. So what might you look at this and say? Well, thinking about the relationship between order and any integer, such that when you exponentiate a to it, you get 1 mod n. We know that exponentiating a to its order, mod n, gives 1, right? Because the order is defined to be the smallest number for which that happens. But if some other number does that, all we know is that the order is smaller than it, right? But this method tells you that there's something else you can say, and it's that the order divides that exponent, right? It's that exponent has to be a multiple of the order. And that is the following theorem that has a very easy proof and is very straightforward, but is actually pretty important for this. So it doesn't have a name in the book. I'll just say it has to do with order, right? So this is our theorem concerning the order. Our definition of order doesn't refer to anything other than it simply being the smallest exponent for which this happens. So then this theorem says a little bit more. So let n be a positive integer, a be an integer such that GCD of a and n is 1. Okay, let m be an integer. Then a to the m is congruent to 1 mod n if and only if the order of a mod n divides m. Okay. So the backwards direction was just obvious. I'll write it out anyway, but the backwards direction was obvious. But it turns out the forward direction is not too bad at all either. So what's the proof of this? So let's do the backwards direction first. So that is the order divides m. That gives you this, right? So let's say let m naught be defined to be the order. Just don't want to have to write this a bunch. It's kind of a clunky notation. So let m naught be defined to be the order of a mod n. If m naught divides m, then just by definition of divides, m is equal to m naught k for some k. Thus, a to the m is congruent to a to the m naught to the k, but we know that a to the m naught is congruent to 1 mod n because m naught is the order of a. So not only do we know that, we know it's also the smallest such integer. That doesn't really matter right now. So that will matter in the other direction. So this is 1 to the k, which is 1 mod n. Which is exactly what I wanted to show. So forward direction, suppose a to the m is congruent to 1 mod n. Okay. So write using the division algorithm. Right, m is m naught q plus r. So divide m by m naught. You get that you can express m as m naught q plus r, where r is, of course, bigger than or equal to 0, but also strictly less than m naught. Then a to the r is, I can sneakily rewrite that as a to the r times 1 to the q. Now, why do I want to be tricky with this? Well, 1 to the q is also a to the m naught to the q. So this is a to the r times a to the m naught to the q. So a little algebraic trickery there. Okay, which means that this is a to the m naught q plus r. But this is a to the m, and I've assumed that that's 1 mod n. Okay. But m naught being the order, right? But m naught is the smallest such thing. Such positive integer. So this bound on r, since r is strictly less than m naught, means that r has to be equal to 0. But if r is equal to 0, that means that m is equal to m naught q, i.e. m naught divides m. That is, the order divides m. That's it. Okay, so pretty straightforward and simple proof. And this fact, you again, just working through like a single example, like we did before, might tell you that you kind of understand what's going on with order here and why this is the case. But even though this is a very simple fact, this is actually going to be pretty powerful for being able to. I'm going to use this because this was used by Euler to factor some large number that was thought to be prime. Okay, and we'll see how this works. Okay, we'll apply this both to Fermat numbers and to Mersenne primes. Okay, so there's a corollary of theorem that says the following. So actually, it really says one thing. This first thing I'm going to write is a special case of the second thing, but because this thing is nice in particular, I'm going to stress it. So let P be prime, and let A be not congruent to 0 mod P, or let P not divide A, right? Then the order of A mod P divides P minus 1. Okay, it turns out a more general thing is true. Let n be positive integer and GCD of A and n be 1. Okay, then the order of A mod n divides phi of n. I mean, I can immediately prove 2, which means I've proven both of these things because if P is prime, phi of P is P minus 1. So these things match up directly from the theorem. I can prove this, right? So quick proof. Note 2 implies 1, so we only prove 2. Okay, but all I have to do is by Euler's theorem, A to the phi of n is congruent to 1 mod n. Right. Apply the order theorem. And that's it. Right. The order theorem says whenever you have an arrangement like this, whatever this exponent is has to be divisible by the order. So the order has to divide phi of n. That proves 1 because when n is a prime, that's what pops out. Right. Okay. Okay. Quick example, and then we'll move on to an application of the order theorem to places where it might not seem immediately like it would have any business being applied. Okay, so I want to compute the order of 3 mod 23. Okay, so note we could compute 3 to the I mod 23 until we get 1, right? But that's, that could take a long time, right? You're not guaranteed that this is, I mean, well, you have an upper bound, right? It's phi of n's the upper bound, so maybe it wouldn't take too long in this case, but in general, right? Just try to do it a brute force way would be no good. So by the corollary, we know that the order of 3 mod 23 divides 22. Right. And we know that from the first part 1. So this is 1 of the corollary. Okay. So if this order divides 22, there's not a whole lot of options here. So this order of 3 mod 23 is either 1, 2, 11, or 22, right? Because its prime factorization is 2 times 11. Okay. But you can actually just compute some of these, right? So, 3 to the first is not congruent to 1 mod 23. And 3 squared is not congruent to 1 mod 23. Right. So we try 3 to the 11. If that doesn't work, I only have one more possibility. I don't even need to try it. It can only be that. But let's try 3 to the 11. So 3 to the 11 is... I can do this by squaring. So this is 3 to the 8 times 3 squared times 3 to the first. Successive squaring can compute these really quick. So 3 squared is 9 mod 23. I'm not going to write the mod 23 over and over again. So 3 to the fourth is 81. So mod 23, that's 12. And so 3 to the 8 is 144. Mod 23, that's 6. Right, so this is congruent to 6 times 9 times 3, which is in fact congruent to 1 mod 23. So the order is 11. Because that's the smallest possibility in this list. Okay. All right. Okay. So, cool application of this fact. So, let's return to Fermat numbers. To see an application of the order theorem. Okay. So remember, the Fermat numbers are 2 to the 2n plus 1. Okay. So the first few, there was f sub 0, which is 3. There's f sub 1, which is 5. F sub 2 is 17. F sub 3 is 257. And F sub 4 is 65,537. Okay. Now, the thing is, all these are prime, right? So these are all prime, which is what led Fermat to say that he conjectured that all of them, for any n greater than or equal to 0, these are always prime. Of course, the first counterexample to this is f sub 5. And although these Fermat numbers have been shown to be not prime, I think all the way up to n equals 32, they have only been factored up to n equals 11. So actually coming up with a prime factorization of these is kind of hard. And so f sub 5 is going to be a big number. So showing that it's not prime, and especially coming up with a factorization, can be pretty hard. But so Fermat believed, as I mentioned before, Fermat believed that f sub n was prime for all n greater than or equal to 0. But Euler showed that f sub 5, which is, if I write out the digits, 429496, 7297. Well, that number kind of looks prime, but it turns out that this factors as 641 times 6.7,417,000. Okay. All right. So, the question is, how did Euler do this? Because while multiplying these, of course, by hand, you could do that if you had enough time. It's kind of annoying, but you can do this. So the checking is easy, right? But how do you factor something like this? It's a complicated thing. Factoring a number this big is a really, really hard thing to do. And Euler did this in 1732. So 1732, Euler did this thing. 1732, 34, 32, yeah. Okay. So the answer is the order theorem. Okay. Now, there's a proposition that we're going to prove that follows from the order theorem. The proposition we're going to prove is like one factor of 2 better than the one that Euler used. So ultimately, the process that he used to do this was slightly more inefficient than what we're going to do, but only very, very slightly. So it's essentially the exact same thing that he did. Okay, so it turns out there's a proposition that follows from the order theorem that's going to help us. So it turns out that there is a proposition that follows from the order theorem that helps us here. Okay. All right. So what is this proposition? So here's the following proposition. So let n be greater than or equal to 2. Let p be prime. Dividing f sub n. Okay. Then p is congruent to 1 mod 2 to the n plus 2. The fact that Euler used didn't get that p is congruent to 1 mod 2 to the n plus 2. It got the slightly less strong fact that p was congruent to 1 mod 2 to the n plus 1. Okay. So anyway, that's the deal. So we're going to have a slightly sharper result here to use, but it's not a significant difference. So how does the proof of this go? Well, if p divides f of n, and f of n, of course, is 2 to the n plus 1, right? Then 2 to the 2 to the n is congruent to minus 1 mod p. Okay. But I can square both sides of this. So squaring both sides, what do I get? I get 2 to the 2 to the n plus 1 is congruent to minus 1 squared, which is congruent to 1 mod p. Right. Thus, by the order theorem. Let me remind you what the order theorem said. Right? It's that whenever you have an arrangement like this, a to the m is congruent to 1 mod n, then the order of a mod n has to divide m. Okay, so that's by the order theorem. The order of 2 mod p has to divide 2 to the 2n plus 1. Oh, sorry. No, it does not. It absolutely does not have to divide that. I was recopying this. It's this that it has to divide. So that's 2 to the n plus 1. Okay. All right, now we have a correct statement. i.e., since the order 2 mod p has to divide this, what does that mean? If it divides a power of 2, then it also has to be a power of 2. Right? So i.e., the order of 2 mod p is a power of 2. It's 2 to the j for j some positive integer less than or equal to n plus 1. Note, if j is actually less than or equal to n, then 2 to the 2n is congruent to 2 to the 2 to the j to the 2 to the n minus j. Well, why can I do this? You might say, wait, you could always do this via just algebra of exponents. But if j is not less than or equal to n, then this could be negative, and you can't do that, right? You need this thing to be non-negative. So if j is less than or equal to n, then this exponent of the 2 here is non-negative, so you can do this trick. Okay, and you don't get any problems arising. But 2 to the 2j, since 2j I'm calling the order, has to be 1, right? So this is 1 mod p, so this is 1 to the 2 to the n minus j, so that's 1 mod p. But that's a problem, right? This is a problem because I've already said earlier that 2 to the 2n, just from p dividing 2 to the 2n plus 1, this Fermat number, 2 to the 2n is congruent to minus 1 mod p. Right? So this is contradiction. So contradiction. So where did my assumption go wrong here? My assumption went wrong at this step where I said let j be less than or equal to n. So j has to actually be n plus 1 here, right? i.e., the order of 2 mod p can't be 2 to the j for some j less than or equal to 2, less than or equal to n plus 1. It actually has to be 2 to the n plus 1. Okay. By the corollary to the order theorem, this means that 2 to the n plus 1 divides p minus 1. Why does it say that? What is the corollary of the order theorem? So, here. Corollary of the order theorem says if we have p of prime and a not congruent to 0 mod p, that is p not dividing a, then the order of a mod p is it divides p minus 1. So the order of a mod p here, which we've said is 2 to the n plus 1, has to divide p minus 1. Right. Okay. But 2 to the n plus 1 dividing p minus 1, that just means that p is congruent to 1 mod 2 to the n plus 1. So this is what Euler proved. He got to this step and he stopped. Okay, so here's where Euler stopped. So his proposition looked slightly different. It was exactly this statement, except it was P is congruent to 1 mod 2 to the n plus 1, which is what we've gotten here. Okay, we can do better than that, though. So we are going to do slightly better than this. And we are going to do this by hand waving a little bit. Okay, so we could stop here, and be happy, but with a tiny amount of hand waving to be cleared up in chapter 13. We can do better. Okay. So what do we have? Let's keep going with this proof. So proof continued here. So we have P is congruent to 1 mod 2 to the n plus 1. We want P is congruent to 1 mod 2 to the n plus 2. Okay. All right. Note, P is congruent to 1 mod 8 since n is greater than or equal to 2. So then it's congruent to 1 mod 2 cubed. All right. So via exercise 31 is the exercise 31, is that, I can't remember if that refers to chapter 11 or not. I don't think it does. I think it actually refers to, let's see here. Yeah, it does. So chapter 11, exercise 31, which I'll assign in your homework 4. It will be assigned as a package later. So I'll make an announcement about that later. So via exercise 31, which is in chapter 11 and chapter 13, there is a thing that we need. We'll show that there exists a b such that b squared is congruent to 2 mod p. Okay, when p is congruent to 1 mod 8. Now, this is a statement that is starting to touch on some serious stuff. Squares mod p, that is finding when you can find an integer that is a square mod p. That is that's an involved question that chapter 13 specifically deals, that's all that it cares about. And this is where this fact I've mentioned before, quadratic reciprocity, raises its head. So squares mod a prime is something that's important, and I'm not going to get into that in the rest of this proof. Just know that for now there exists a b that satisfies these things. Okay. All right. So how does this help us? So then repeat our previous steps. With b replacing 2. Okay. So let b, which is b squared is congruent to 2 mod p here. So in our previous steps, just let b take the place of 2. So then b to the 2 to the n plus 1 is congruent to b squared to the 2n, which is congruent to, since b squared is congruent to 2 mod p, this is congruent to 2 to the 2n, which we already know is congruent to minus 1 mod p, right? And b to the 2n plus 2, or sorry, 2 to the n plus 2, is congruent to b squared to the 2 to the n plus 1, which is congruent to 2 to the 2 to the n plus 1, which is congruent to 1 mod p. Okay. So notice how this mimics what we did here. Okay. All right. Thus, the order of b mod p divides 2 to the n plus 2 and does not divide 2 to the n plus 1, i.e. the order of b mod p is equal to 2 to the n plus 2 by the corollary to the order theorem. The order, or the order of b mod p, which is 2 to the n plus 2, divides p minus 1. Okay. i.e. p is congruent to 1 mod 2 to the n plus 2. Oh, there we go. Okay. Then one more thing, we'll see how we actually can apply this, and we'll be done with lecture. So here's how Euler did it. Okay, so we have f sub 5. Okay, so we want to try to find prime factors, right, if they exist. This proposition says if they exist, there's some restrictions on them, right? So any such p must be congruent to 1 mod 28 by the proposition, right? Okay, so the primes that are 1 mod 128 are, I can just start making a list of them, right? So 257 is one of them, 641 is one of them, 769 is one of them, 1153 is one of them, 1409 is the next one, and so on. Okay, so I get a list. Now I just need to check by hand, right? But 257 doesn't divide f sub 5. You can check that by hand. Okay. But 641 does. So we have found a prime factor of f sub 5, and so f sub 5 is composite. So I'll continue here on Monday, because there's another thing that I want to say to kind of round out this discussion of how this applies, because we're going to do a similar thing for Mersenne primes, or Mersenne numbers, rather. So this is an example of how relatively straightforward application of the definition of order makes some of these practical matters, like trying to actually find a prime factorization for F sub 5 or F sub 6 doable. It actually makes these things doable. And I'll explain, what it is that basically goes wrong for the larger F sub n numbers. Anyway, so that's all I wanted to say. So as I mentioned, I'll be, let's see, it's 12:25 now. So hopefully by like 3 p.m. today, I'll have made my big announcement that'll include your exam 2 that'll be due on Monday and the small complimentary homework 4 batch. So anyway, so be on the lookout for that. I will have made a post on Elms by 3. As I mentioned previously, office hours are going to be moved to Monday. That way you've had a weekend to look at those problems. So if you have any questions about them, you can ask me during office hours on Monday. Also, if you have specific questions about how your exam 1 was graded, you can ask. I don't expect there to be too many issues there since everybody did really well. But anyway, so yeah, if you have any specific questions about any of that stuff, you can ask me during office hours on Monday, and they'll be the same time. They'll be 2 to 3:30 on Monday. So I'll include all that info in my announcement later. So anyway, I will see you all on Monday. I'll be around. Like I said, look out for the announcement here in a couple hours.